So I appreciate everyone's time. As alluded to, my goal here today is really to kind of evoke some thinking on a new way of going about protection potentially, and how you actually go about protecting what you've built in terms of endpoints and systems. This construct and concept is not relegated to a Windows machine or a Linux machine or something like that. I want you to think abstractly and conceptually about this as we go through it. And then of course beat me up with questions at the end. All right, so I want to start with this. This is actually a real diagram of the number of applications in an enterprise. Now it could be government, non-government, commercial, et cetera. But this is fundamentally what I feel the problem of defense is today. It's not about picking the right technology or tool. It's about how do you deal with complexity. And complexity as a human, as us, as individuals, is hard, especially when you're dealing with a non-physical world. Right? Over hundreds and hundreds of years, we've developed these unique senses that when you walk down an alley, you just the hairs prick up on your neck, maybe something's gonna go wrong. There's all kinds of things happening in your subconscious, analyzing data, information, et cetera, to make a risk perception for you immediately. Well, you don't have that when you're looking at a web page on Google, right? All those things are gone. So complexity is really the issue that we have as defenders. And sadly, the world is getting more complex, not less complex. So you have a situation as a defender, where do you start in this whole piece, right? Let me make sure I got my pointer here. And do you start in your own security tools, because they have problems too, right? Do you start in the core of the network with your infrastructure, your applications, or do you talk with your third-party folks that can also bring issues? They're all risks. Every organization is a different risk. Where you choose to start, as alluded to earlier by Oren, usually is what ends up protecting your organization or not. You pick the wrong spot, you have your 5-year roadmap, and next thing you know, you're way off into year 3, focusing on the wrong thing. Like for example, the one client I dealt with a few years ago that put laptop encryption on all of his laptops across the whole bank when he was using Citrix to access everything. So there was no data on the laptop to encrypt anyway. But nevertheless, right? So making bad decisions is a problem. Now, I was a CISO at a large energy company for many years, and we fundamentally, I think, boiled everything down to a big problem, a needle in a needle stack problem. We had too many threats to deal with. We didn't know which one was the right one to be focusing on with our limiting resources. So we started looking at this complexity problem in a different way. And so I want to present some of what the best of the best get when they do defense the right way to see how bad really defense is right now. So this actually came from a 2011 study. I couldn't get new numbers. I apologize because the study hasn't been done again, but it gives you an idea that the best cyber defenses at the time, they were able to reduce things like the return to a trusted state, meaning we now know we are secure enough again to continue operations, was 18 days, right? So for one organization that could kill you, in a mission, that could be the end of the mission, right? Whatever it may be. Costs, of course, are significant. But as the threats change, so do the number of days to get back to a state of trusted, right? Now, I don't really think this has gotten any better. Matter of fact, I think it's gotten worse than this 2011 study most likely, because it's Internet of Things we'll talk about later, et cetera, right? So even if you do defense right, this is where you get to. This isn't good enough, right? So you got to do defense better. And I actually harp a lot on when I talk on not exploits, not offense. That stuff's cool and sexy. But in the real world, as I say, we're all defending ourselves. We have to deal with things like budget and people and politics and bureaucracy and those type of things. That's what you have to deal with. So I started having a conversation with a buddy of mine over drinks, and a few scotches in, next thing you know, we start talking about other things. And this is a photo of my city, Chicago, okay, where I'm from. And the gentleman actually is a friend of mine. He's not in security. His company, he's a son of a gentleman who owns a large construction company in Chicago. And we're sitting here and I'm talking to him about complexity, and he's just ignoring me mostly. But he goes, we build these complex things all the time. My dad does, and buildings don't fall down. He's like, why can't you IT guys figure this out? He's right, these buildings are super complex. Look at skyscrapers. They don't just fall down in the middle of the day. How many networks fall down in the middle of a day from one phishing email? Most of them, right? So we have these complex networks that have no resiliency at all. So I actually kind of took that as a comment and started doing some more and more research and understanding how is it that in other trades, mechanical engineering, chemical engineering, et cetera, they go about complexity. And here's what I found. First, going back to the building analogy here, anybody know of the last time a building just randomly fell down? Happen to know? Maybe any, engineers in here? No? It was actually about 15, 20 years ago in India, a mall collapsed in the middle of the day. And it was actually simply because they knew it was going to collapse and the owners didn't want to tell anybody because it would shut down the mall, right? But in general, we've got lots of processes in place to determine when things are going to fail in the construction world because, very simply, it impacts lives, right? If a building falls apart, people die. In a cyber world, if somebody clicks on a Michael Jackson death link on Google and goes to a page to read about Michael Jackson's death and gets hacked 3 different ways, does anybody die? No. And so I think, sadly, some of the ways we approach things are very differently. So I started looking at these building construct concepts and saying, what can we learn from them? And here's what I learned about. Anybody heard about failure mode effect analysis? Maybe go back to your college days. Raise your hands. Anybody? A couple people? Okay. So I'm going to reintroduce you to this concept, but more importantly, I'm going to reintroduce you to this concept in a way that you've probably never heard of before, which is for cyber defense. This concept and this process is usually used for fancy things like buildings, but also very, very complex systems, all right? So FEMA is actually a process for identifying failures in a system, no matter what that system is. The intent here is to understand what is potentially possible, right? So this is not a process about identifying all the potential risks. It's not a process about identifying what could go wrong. It's a process of knowing if something goes wrong, how do I detect that failure, okay? So it focuses, too, on one important thing that we don't talk about in cybersecurity enough in my mind, which is the actions after the attacker gets in. Everybody likes to talk about exploits and newest, coolest, latest way somebody got in. But what do they do after they get in? I like to look at that piece of the puzzle. So quick history on this. This was first used in the 60s in the aerospace industry. Complex system, right? Sending rockets and planes into space, et cetera. The Navy actually standardized on this with a standard here, so if you want to go read about that, you can. Then the automotive industry jumped in on this and said, wow, this is really cool. We're building more and more complex cars. They got millions of lines of code now. We need a way to make sure things don't go wrong and kill people, right? So they started adopting this approach, right? So here's an example of that. Let's say we want to make a Molotov cocktail and we want to blow up a building. What are the things that we need to make this thing successful? One, we need a bottle, we need some alcohol in it, we need a rag, we need oxygen, we need the rag to be in the actual bottle so that it has alcohol on it, we need to light it, we need a window to throw the thing through, we need the ability to throw it, and then of course we need to hope that there's oxygen on the inside for the whole explosion to occur in the first place. If any one of those conditions do not exist, the Molotov cocktail will not work. If there's no oxygen, no flame. If there's no striking of the match, lighting, et cetera, nothing's going to go on fire. If there's no window, we can't throw it in there, right? So the idea of testing conditions is the core fundamental process of FEMA, all right? So the idea is we don't look for the potential risks out there. We don't look for exploit code in memory, et cetera. We look for the things that can run the exploit code. We look for the things that essentially are failures in the way the operating system was intending to work. So in our case, going back to the Molotov cocktail, we could look for a flame, we could look for heat, we could look for a window being broken, all different types of conditions that if triggered would indicate that something went wrong. Now in most networks, where do we put our detection mechanisms? Usually it's an IDS on the edge. That's not where the attacks happen though, right? We heard Oren earlier about it's the endpoint. People are getting phished on their workstations, their laptops, et cetera. It's inside the organization. We don't have any detective mechanisms generally on endpoints at all. We usually don't even have a way after we detect something's got in to even go back and look what happened. We've all heard about forensics, of course, but forensics is hard, it's difficult, it's time consuming. It's also very, very fraught with error if the certain conditions at the right time weren't set up. So what are you going to do if you're a defender and you've got all these different types of things to look at, you've got a bunch of alerts coming in, which one do you focus on first? Maybe you should focus on the one that, if it did occur, is going to give access to or potentially impact more failures going down your entire organization. So let's extend this example a bit forward. So this process of testing conditions happens kind of forever, but I've actually done this process. So I'm not just giving you theory here. I've worked with this process now for about 4 years or so, I believe. And this process really is about identifying the next stages of failure. So for example, and let's talk about it, a SQL injection attack occurs, a database or a web server is compromised. What's the next failure that could happen? Attacker could maybe stay on that machine, they could pivot, they could go after a different machine, et cetera, right? You look at each asset individually and start looking at the failure modes that they can all occur. So I'll give you a real world example of this when I was running that energy business. We did have a phishing attack. Was it 100% of attacks are phishing? We had a phishing attack. With a 0-day, though, PDF exploit, targeted to a certain person. They were out in the field. They actually managed a substation in the middle of nowhere. But they had access to confidential information that a certain state wanted, right? And so they targeted that person through LinkedIn, sent them a phishing email, popped their box. Now, we had all kinds of detective controls at the network side, right? But here's what happened. The attacker got on the machine. They never had to move. Why? Well, because we didn't really do things right in terms of our policies, and we allowed administrators to log into machines. And if anybody knows, if you're an administrator and you log into a computer, it caches your password there. So the attacker didn't have to go crack into a domain controller or break into the network or move around or do all these different things. They just had to actually crack the password on that computer right there. Once they got it, they were full domain admin, full access to the network like everybody else. So they immediately now went from being an attacker, we could maybe detect some anomaly, to being a normal user. All right, they started going around the network, looking at data, boom, got what they wanted, sent it out, took it. We actually did identify when they started sending the data out, so we started shutting things down. And that's when they got really upset and started deleting virtual machines on us because they had access to our infrastructure, right? Now, when this whole process was occurring, what were you doing? We were running around like crazy, right? Our incident response policies and process went out the window. We started focusing on what do we do? What's next? What's going to happen here, right? Later on, we actually went through this process of doing the failure mode analysis, and you start documenting what are the things that you have to occur for an attacker to move between different areas, right? Move between network segments, for example. Move between different applications. And that documentation process ends up giving you the exact same things you need to look at to determine during an incident if an attacker has moved into a certain area. So now I know what it takes for them to move. I can see if they have moved. So if we look back on that incident, we did a mock incident with the same thing, going through this exercise first. And we uncovered that we would have seen them actually starting to log into all these different shares if we had actually looked for administrative users logging into shares. Because that wasn't what's common, right? We would have seen this, we would have seen them moving across the network because they actually transferred gigabytes of data across the network, but we never looked at the amount of data that we transferred between systems. We found a bunch of different things that we would have been able to detect them much sooner, right? It all came from identifying the conditions that have to exist for the attacker to actually execute their attack. Now, I'm going to wrap up here with kind of two things and go into questions about implementation and how this actually works. A really good example of this, since we're here talking about kind of government and NASA, et cetera, is actually the Mars Spirit rover. Many people don't realize that it actually kind of broke one day. It stopped functioning and started sending a distress signal. And one guy had thought of, way back, did his failure mode effect analysis process and said, you know what, there's a possibility that something's going to go wrong and that Mars device can't boot. What are we going to do if it can't boot? And so he put in a custom state to allow it to go into a crippled mode that allowed you to reinitialize the firmware and basically re-image this device millions of miles away. And sure enough, it didn't boot in the middle of space. And it failed back to its crippled state, and they did a firmware upgrade all the way over, rebooted the thing, right? This was a direct interaction of their failure mode analysis. Now, this was taught in schools for many years, in engineering schools, using this process. You guys may have seen this if you've ever did any Navy training, but this is actually a sample of if we had an attacker going from the top all the way down to the bottom, and the only way they could move is with horses. How do they go from the top to the bottom, and how many horses would they need? And you kind of go through an exercise of what's the process from going from one step to the other. And it's really just a training exercise in conditions. What conditions have to exist at station 3 versus station 4 for the attackers to move to the next station, right? Now, there are some fancy ways you can take this process and go very quantitative. I actually feel that quantitative types of approach for this usually don't get as good results. This process actually ends up becoming a probability problem. So the math guy in the audience is probably excited about this. But you can actually do probabilities for every single condition, the likelihood of a condition happening. You can multiply and do this stuff with probabilities and come up with a nice cool score that says, we're 71.3% likely that this condition is going to happen. In general, I find that approach, while it's cool because you have a lot of good numbers, doesn't necessarily mimic real life. But the point I want to get across here is that this is a simple thing you can do. This is not complex. I've worked with junior level IT folks all the way up to CISOs during these exercises we'll talk about, and it works very well. So what do you do? Well, first, you start with a simple asset. You draw your network map on a whiteboard, okay? Pretty simple process. You don't have to go crazy in your network map, just a simple one. You say, okay, where's the thing that we want to protect? You pick one. You have many things you want to protect, so just pick one. You take that one item, and you say, okay, the attacker's outside here. How do they get there? You pick each asset along the way, and you just talk to each other, and you say, okay, what's the chance that they're going to go from this machine to the next one, and how would they do that? And you write it down. Simple list. SQL injection is possible, maybe here. We know that this isn't patched. We know we have weak passwords here. We know we have this, okay? You're essentially going to start to build an attack chain to that asset, right? But you're focusing on things that are realistic, failures that can actually occur in your organization. So first you start with the input. You take each failure mode, for example, a SQL injection, elevated privileges, et cetera. Then you go ahead and identify the causes of that failure. So this could be an exploit. It could be weak hashes. It could be policy. And then you list the current controls you have to detect that, and that's the key. That's the difference between this process of failure mode analysis versus every other security process. You actually integrate what you can do well into this analysis process. Every organization does things well differently. Some are good at detecting network attacks. Some are good at detecting endpoint attacks. Some are good at doing nothing, right? And we know if we can't do anything well, then we have a totally different approach we have to take. But if you know that you're able to detect invalid logins very well, you have good processes, technologies, and systems for that, then that's going to go ahead and change the potential for you to detect that failure. If you're not good at it, you get your list of things you have to do better, all right? So now you can go ahead and go quantitative, as I mentioned, calculating what's called a risk priority number. And I'm using the official terms here in case you want to take this slide deck and search on Google real quick. There's lots of information on this for other industries, mechanical engineering specifically, as well as structural engineering. Once you have your list of conditions, and again, I do this on a whiteboard, we're talking simple list of conditions, usually no more than 10 to 15. You start seeing this per asset, you start seeing the frequency. Wow, we see privilege issues on this one, this one, this one, this one. So 5 of the 7 assets that get to our critical data have a privilege issue potentially or failure potential. That frequency is a good indicator of what's likely an attacker is going to do. As we alluded to earlier, attackers are not sophisticated, they're effective. And how do you be effective? You reuse what you already know over and over and over again. And so majority of attacks, Brian Krebs, anybody read Krebs on security here? I assume so. He just did a great post last week about the target breach and the actual exploits that were used and the processes that were used. They were like 4-year-old exploits. I mean, these were rock solid, amazingly effective exploits for SQL Server, et cetera, that tons of people had used. There was nothing special, 0, right? So once you develop this list and you kind of get your frequencies, if you do use the quantitative approach, anything with a 10, and I'll give you an example of a quantitative approach here in a second, is what you should be focusing your efforts on. Anything else is really based on frequency, how often you see these things in the environment. So walk through this process. Here's the mathematical approach, just so if you want to see it. You assign each of these conditions a severity. So if this condition fires, what's the impact to the organization? So if the privilege escalation occurs, is that a high impact or a low impact? If injection occurs, high impact or low impact? The occurrence, so how likely do we think this is going to occur? Good example, different customer I worked with had 400 applications in one data center. Right, 400 different custom-written applications in one data center. Their occurrence of an application vulnerability was a heck of a lot higher than the company down the street that had 10 off-the-shelf applications. Right? So different occurrences matter. And then our ability to detect, lastly. So for each of these, what's our ability to detect this condition happening? And you go from a 1 to a 10. You just multiply these. Right? Very simple process. So I'm going to leave it there for questions. Now, the reason I kept this abstract and I didn't talk about specifically a system or a device or whatnot is it's irregardless of if it's a SCADA device, a server, you name it. I use this approach on a multi-100 SCADA device network that had gas valves controlling whether things blew up or not. Okay? And it worked for individual valves, it worked all the way up to systems, and it's now worked for a while for various clients regardless. The key result of this process is to focus on the things that you can defend, to focus on the things that you don't defend well and continue to make process and improvements on them. I think too many times organizations become good at doing one type of defense and they just keep doing that and getting better and better at that, when in actuality they're going to completely be blindsided by something else, right? And so most organizations, most CISOs specifically, have no idea what they're good at and what they're bad at. Going through this process allows you to see what failures you're going to handle effectively and what failures you won't handle effectively, then hopefully change your view on things. So if you do this, what I've seen is those numbers before change, okay? And here's how they change. When you have a documented list of potential failures for key parts of your network, when you are under attack, you know exactly what to look for immediately. You can go right to that system and go, you know, we determined that it's likely that privilege escalation is going to occur, that we're going to have data exfiltration in this area. Have we seen those happen yet? Yes or no? You go look, you find it, you make your decision, you move on. It ends up becoming almost more so like an initial checklist process to get the cruft out of the way so you can focus on this attack if it's unique or not. Right? If it is unique, then you have a different set of process. If it's not unique, you can now deprioritize this, have your level 1, level 2 people deal with it, and move on to the next one. And in this world of volume of threats, if you don't have a structured way to be able to quickly identify if this is the big needle that's going to stab you in the heart and kill you, or just a pinprick, you're always going to be running around like crazy. So, any questions?